Hello, everyone. Thank you for joining us today for recent advances in wearable sensing devices with a focus on epidermal skin technology and health monitoring. My name is Nicole Navratil. I'm going to be your moderator today. I'm just going to go over a few housekeeping things before we get started. There's a Q&A button at the top of the toolbar, the top of the screen. You'll see it has like two little bubbles and Q&A. You can submit questions there throughout the presentation, and we will go through the questions at the end. If we run out of time, we'll go through all of the questions and make sure they get answered and follow up with you directly, and also post a summary of the Q&A on our website. Please feel free to use the Q&A in the chat if you have any other issues. I'll be monitoring this throughout the presentation. Also, this webinar is being recorded and it will be distributed following the session. So with all that, let's get to the good stuff. I'd really like to introduce our guest today, Dr. Jessica Koehne. She's a physical scientist at NASA Ames Center for Nanotechnology. She has a PhD in chemistry from UC Davis, and at NASA, she's been developing carbon nanofiber, carbon nanotube, and graphene-based sensor platforms for detection of DNA, RNA, proteins, and neurotransmitters. She has significant experience in device fabrication, including nanomaterial growth and integration, surface chemistry, electrochemical characterization, and sensor validation. She currently leads the highly interdisciplinary nanobiosensor team, and her work has applications from astronaut health monitoring using implantable and wearable sensors to the detection of life signatures within planetary exploration. So with that, Dr. Koehne, take it away.
Yeah, thank you, Nicole, so much for the kind introduction. Let me see about sharing my slides. Oh gosh, now where is it? Everything, okay, here. Everything looks different all of a sudden here. Hold on one second. There. Aha, okay. Everyone can see my slides? Okay.
Yes.
All right. Well, thank you again, Nicole, for the introduction. I am going to talk to you guys today about this space of wearable sensors for, and in my case, for human health monitoring for NASA missions. This is going to be a little bit of a NASA-centric talk because that's where I come from. And so I'm going to tell you a little bit about our motivation for why we're in this space, our motivation for technologies for sustained human exploration, introduce you to an idea of in-space manufacturing, which is going to guide a lot of the development that I'm going to show you today, and then talk to you a bit about some of the printed sensor technology that we have under development, and end with one such device that's being developed right now for future NASA missions. So at the moment, we're kind of in this interesting transition period where we're looking to leave the International Space Station is planned to be decommissioned in 2030, which is not very long away from now. And then from leaving the International Space Station, we are on our way back to the moon with the Artemis missions that have already begun, and bringing humans back to the moon. And the moon really being a testing ground for how sustained of a presence can we have, and using that kind of learning and know-how and technology development to eventually sustain human presence and human exploration to the Mars surface. So a little bit of what's motivating some of the development by a lot of us at NASA, and in particular also my lab. We've been looking at how we use the International Space Station currently, and we've looking at what we have on the International Space Station that eventually breaks, fails, and needs to be either repaired, replaced, something brought up from Earth. So there was a National Research Council report that came out in 2014 that looked at such hardware failures on the ISS, and they broke it into this plot, that you can see where they kind of group things in different categories. And what you see in this area, or the yellow part of the pie here, and the largest part of the pie is failures in the electronic space, electrical systems in particular. And so these are parts that once they are more commonly failing, will then need to have hardware either sent or replacements sent to make these systems run again. So if we look at how we do that on the International Space Station, we really rely on ground support at this time. And the International Space Station, while it seems very far away, it's actually relatively close. And we have spacecrafts going back and forth, bringing supplies, bringing crew members back and forth quite commonly. And if we look at the International Space Station in terms of what we carry a large mass, and these are all kind of shown here in these green squares of different supplies and replacements that we'll carry around at any given time. As something fails, we'll have a down mass of something that we'll get rid of, and then we have a storage of spare parts, which is also represented in squares of mass on the ground, that we can then take to resupply what we've taken, say, off of our storage shelves on the International Space Station. So there's a constant resupply that happens on the International Space Station currently. This works really well for the International Space Station. It's relatively close to Earth, and so this has been a good system, but it's not going to work for us in the future, and it's not really conducive to long duration, deep space exploration like going to Mars. And so we're going to need to look at a new way to think about how are we going to deal with things when they break. And that has kind of led to this idea of bringing manufacturing capabilities to manufacture parts, repair parts as you go, instead of having so much redundant mass along the way of spare parts. So this is a big paradigm shift and how we're kind of thinking about these architectures, and something we'd like to test out, especially as we start these missions, these Artemis missions to the moon. And so the idea of going to in-space manufacturing really allows us to optimize the resources that we take along. Oops, sorry about that. So we will make on demand what we need instead of bringing a large assortment of things we might need. And it decreases our dependence on the supply chain. We're not going to have to bring things from ground so much, and therefore also decreases the launch costs. So we think this is a viable approach moving forward to deep space flight. This concept of in-space manufacturing has a lot of investment areas within the agency, and this chart is just showing you a lot of what's going on in this space. And just to highlight where I'm coming from is this area of printed electronics, that we are looking at manufacturing capabilities that can aid us in this space. Okay, so that was a lot of talk that was just kind of setting the stage a little bit for NASA and the impetus for how we're going to be making things, and the kind of follow-up slides here. But now I kind of want to bring us into why we're looking at these health diagnostic devices to support human space flight. I'm sure that everyone's probably, at least peripherally heard that the space travel puts a lot of stresses on the human body. There's changes, of course, in gravity. We're in microgravity. There's higher radiation exposure that can happen, especially as we leave lower Earth orbit. And so there's a lot of physiological systems that we are are critically important for us to be able to monitor in real time and to ensure the health and well-being of our flight crew. Here on the right-hand side, I'm showing you some examples of biomarkers. These are biomarkers of interest for things like bone health, heart health, overall stress, muscle health. There's a lot more going on. These are just some of the markers that my lab has been um, um, working on technologies to monitor. And what we really see now is that there's a real need for a point of care. So diagnostic capabilities that can be on flight with the astronaut crew to monitor these things in real time. So in the in the space of wearables, we've actually done wearables, I would say, in the past. And in particular, what I'm showing you is some wearable technology that we employed when we went on the Apollo spaceflight missions. This was a sensor suite that was worn by the astronaut crew. And so it had some, blood pressure cuff, ECG electrodes, various things. But what you'll see is that first off, it's fairly large, but it also has a lot of cables and cords and things to mind as it's being worn. That this was probably not the most simplistic wearable device worn by the astronaut crew. Now, the current development, and this is not happening just at NASA, of course, this is a huge space terrestrially here, as well as the development of very small, wearable, flexible, non-cumbersome biomedical monitoring devices. Our concept is shown right here on the right-hand side, which we're calling AstroSense, is our first prototype. And we're looking at a wearable, also wireless Band-Aid style sensor that can be worn directly on the skin, that can measure a number of different things, but electrochemically addressable biomarkers in particular. And so it's comprised of a 3-electrode electrochemical cell, and is shown right here and will be worn on the skin. I'm not going to show you a lot of development from this device because it's still under development. So what I'm going to do is kind of take you through our process of how we made some of the materials, some of the device structures kind of leading up to this. And then stay tuned. We'll hopefully publish this soon. Our concept here is the AstroSense. We'd like it to be a wearable wireless sensor that has not only sensing capabilities, multiple different types of sensors, being physical sensors, temperature sensors, gas sensors, electrochemical bio sensors, but also the ability to communicate and the ability to have some way to self power the device. So we're looking at energy harvest and storage devices or architectures. We're looking at communication as well. And so the concept would be to have an astronaut who's in this case on the ISS, just going about their business, wearing some sort of sensor suite, which is not really impeding what they're doing, and having interrogators in various places around the workspace. And so we can collect the data without the astronaut having to do anything. They're just able to perform the activities that they need to perform, and the data is being collected all at the same time. So as we started looking at what we wanted to develop in this space, one of the things we first started looking at was different substrates that we could use for our sensor development. We spent some time working on paper substrates early on, and the nice thing about paper is that you can print electronic materials, so you can have electrochemical sensors, but you can also print or mask in a way fluidic handling capabilities. And so we demonstrated a couple of different technologies, one being kind of a fluidic delivery system, as well as electronic materials embedded in paper substrates for electrochemistry measurements. But more commonly, and what we do today, and it's just more common in the field, is working on different plastic substrates. In particular, Kapton is a very attractive plastic material that we use, and we like it because it's physically flexible, it's conformable, so it could be put on the skin as a wearable. It's chemically inert, it's flat, and there's different ways that you can either, purchase the material to have different chemistries on their surface, or you can pre-treat the substrate to have different chemical characteristics. So, for instance, you might want to improve the adhesion of that substrate as you put on your electronic materials, and you can do so very easily with Kapton. We've also, in the space of in-space manufacturing, we've been looking at printers primarily to do all of our manufacturing with. So in this space of wearable sensors, you'll see a lot in the literature of screen printing technologies, which is great. Screen printing we haven't looked at primarily because it's kind of a big process. It's a little bit messy. And so we're looking at technologies that astronauts could have an instrument that they can basically press go and have the instrument do all of the work to manufacture the sensor. And so we've been looking at printers in particular. And these are two such printers that we've been evaluating at NASA for use in our program. And one being precision microdispense, being primarily the Nscript printer. And this printer can print a wide range of viscosities, although they tend to be a little bit more viscous in nature. And you can print on flat, you can print on curved surfaces. This is one example of the Nscript printer printing a device actually for my lab, and this is provided by NextFlex. We've also been looking at inkjet printing. And so there's numerous examples of that, but the one in my lab is shown right here, that we have a DMP 2800 Dymatics inkjet printer. And these printers are piezo drop on demand for ink delivery. And they have a variety of nozzles and a side view mounted camera where you can look at these droplets form and go down to your substrate in real time. These printers typically use very low viscosity inks, aqueous or non-aqueous inks, and print on flat surfaces. And both of these technologies, we've been looking at kind of space versions of them for flight in the future, for microgravity compatible manufacturing for NASA. In addition to looking at printers, we also do some in-house ink development. We do rely a lot on commercial products, but this is one example of an ink development that we did in-house. I work, in the introduction you heard, I work a lot with carbon and carbon nanomaterials. This is a carbon nanotube ink that we've made that's all aqueous. And so we perform a chemical modification where we highly oxidize these carbon nanotubes, and then perform sonication, and we get these carboxylic acid functionalized carbon nanotubes that stay well suspended in just a water solvent for months at a time. And so this is the product that we used on the electrochemistry that I'm going to show you here, coming into the future slides. Once we create the carbon nanotube ink, we also characterize it just looking at the particle distribution. This is really important for your ink developments to make sure that they will actually go through a printer nozzle, as well as the zeta potential. So we look at the surface charge of the inks. And we characterize the carbon nanotubes before and after processing, meaning before and after that chemical oxidation as well as sonication. And what you see is that after that sonication and oxidation, the overall average particle size was greatly decreased, meaning that we had less carbon nanotubes that aggregate once we have them COOH functionalized. Then we created our device. So this is kind of where it gets more exciting here. And so this is what our preliminary device structure looked like, done in 3 different layers using 3 different inks. We first put down a silver nanoparticle ink. This is a commercial ink that we purchased to make these our contact pads, as well as leads that would go to our sensing electrodes. Our sensing electrodes were put down with a multi-walled carbon nanotube layer. That's from the ink that I showed you in the prior slide. And then on top of that, we would put a dielectric layer of SU8. This is also a commercial ink product that we would purchase. And this layer of the SU8 would go and cover up all of the silver lines and leads, and so those don't contribute to our electrochemistry measurements. And the only things that are exposed for our sensing there is the multi-walled carbon nanotube ink and a little bit of the silver that we use as our silver reference. We can look at a camera mounted on our Dymatics printer as we print the different layers. And so you can see this is the silver layer, and then we put the carbon nanotube ink on, and then this is a line showing where the dielectric SU8 ink is print on top. This is, and then here in image F is shown as one such device as it's printed in the lab, and then we have a little custom built electrochemical cell to do all of our characterizations with. And so this is leading up to a wearable. This is some of the development that would take place. So our application that we're interested in here is about measuring stress biomarkers in real time. And stress biomarkers is an indicator of acute and chronic stress. Our biomarker of choice is cortisol. It is kind of the gold standard for stress monitoring. And it's something that can be assessed in the sweat. So it's something that a wearable worn on the skin could actually detect on our crew. We like cortisol measurements by this way because we can do this continuously multiple times a day, which is actually very important to cortisol as cortisol levels shift throughout the day. This is also a non-invasive approach as a wearable on the skin. Other methods for cortisol detection include, from urine, from blood, things that are more invasive that a crew member would actually have to do something to produce a sample to then go and measure. So this is a nice way to do it for our astronaut crew, non-invasively and without them having to prepare something to make these measurements. So leading up to that application and using that device that I showed you on the prior slide, we started doing some electrochemical characterization of the carbon nanotube ink as the working electrode. And we first needed to optimize how much of that ink to put down, that we have a nice conductive film. But we also don't build up so many multiple layers and have it be so porous that we get a highly capacitive sensor. And so this is just showing you some cyclic voltammograms that were taken of a working electrode of different layers of carbon nanotube inks being put down. And this is with just the Dymatics printer which is our inkjet printer, is printing just like your home desk top printer would print. And so we do multiple passes over a print to get multiple layers of that ink down. And so what you see is as we put down 5 layers of ink, we don't see very distinct defined peaks for our redox peaks. And the current's also rather low. As we increase the number of layers, we get this more characteristic shape of our curve, fine peak as well as higher current. And then we typically characterize the output here, looking at the distance between the forward and the reverse scans, We want these to be very small, as well as looking at just the overall current output that we get. From this data with this device, we decided on 10 print layers was suitable for our applications. It was also just a little bit quicker to manufacture. So moving into cortisol detection, again, showing the image of the same electrochemical sensor device. We first immobilized an antibody specific for cortisol on top of that carbon electrode surface. And so this can be done very simply using this carboxylic acid that we created on the carbon nanotube ink before we placed it on the surface. And so performing coupling chemistry to a primary amine on our antibody specific for cortisol, we're able to functionalize that working electrode with cortisol binding antibodies. Then introducing it to cortisol itself will bind to the antibody on the electrode surface. And then what we do is we look at changes of charge transfer resistance using electrochemical impedance spectroscopy. So the charge transfer resistance can be gathered from these Nyquist plots, and in particular, where this semicircle, the inflection point is here. And what we're seeing is that our charge transfer resistance goes up as we bind the antibody to the electrode surface, and this makes sense. We actually have something physically on that surface impeding the electron transfer. And then again, once we bind to cortisol. There's many ways to do this cortisol detection, and I'm just going to say a caveat here right now. We did this as a proof of concept, and we're not moving forward with this particular methodology for our wearable going forward, because we want something that is more reversible, that we can monitor for longer periods of time. So this is just a proof of concept at this point here. So I just want to conclude here that what I tried to show you is where the wearable space can kind of intersect with NASA and NASA missions. And so in particular, this in-space manufacturing, which we find to be a really attractive solution for us with the logistics constraints of long duration human space flight. And that has really kind of dictated a lot of the approach of what I'm creating in my lab. On-demand manufacture of electronics, which is the area that I work in, is offering us tools and methodology for electrochemical sensor manufacturing that is really geared towards manufacturing in an in-space environment. And so the tool development is going alongside along with the sensor development. Then NASA Ames, my lab in particular, has demonstrated a fully printed 3-electrode electrochemical sensor with the inks, the substrate choice, and a proof of concept for cortisol. And I want to end on, these printable wearable sensor devices have a wide range of applications. I know, the large majority, of course, we're interested in wearables for ground applications, but there is room where these can be an attractive technology actually for our space program as well. And so that's what I'm working on. The other thing I want to leave you with is, so many of us in this field, we focus on the sensor itself, and working on these kind of small scale wearable sensors, deployable sensors, used to cause us to also be hardware developers. And what's coming on the market, from multiple sources right now is just a lot of solutions where instruments are being designed for us, and so we have a lot of choice of hardware that we can pull off the shelf, so to speak, instead of being the developers of the hardware as well as the sensor. And that's just allowing us to work on the areas that we do best, that we're most interested in, and working with commercial partners on the other. And so I did want to mention that as I am speaking at this seminar series for Potentiostat manufacturers and providers. In this work, I'd like to acknowledge the data that you saw in this presentation was the large majority, if not all, was produced by Milton Cordero, who is a staff scientist in my lab. Our on-demand manufacturer of electronics project, the PI is out of NASA Marshall Space Flight Center, and his name is Curtis Hill, who's supported this work. I showed you several images that were provided by NextFlex, which is a partner that we have on the manufacturing of these flexible wearable sensors, and especially the development that is going on right now with this device called AstroSense, this wearable sensor suite. And our project lead there is Robert Malakov. And our funding is entirely from NASA, from NASA Space Technology Mission Directorate, under a program that's called Game Changing Development. It's changing its names now, but that's been our funding source. So with that, I should probably, I'm not sure if we're going to take questions now or if we're going to leave it till later, but why don't I pass the mic to Dr. Vyas to lead us from here.
Great. Thank you so much, Dr. Koehne. I think we are going to hold the questions till the end, but please, we've got several that have come in. Please continue to submit those either through the Q&A or through the chat. And I will give a quick introduction to Dr. Ritesh Vyas. He's our Global Head of Electrochemistry Products Division here at BASi Research Products. He holds a PhD in chemical engineering from Lamar University in Beaumont, Texas, with a focus on electrocatalysis, optical sensors, and fuel cells. And before coming to us, he was the international product manager and global expert for Metronome, and he has decades of experience in fundamental and applied electrochemistry. And so he's going to tie our topic together for us.
Thank you very much, Nicole. Thank you very much, Dr. Koehne. It was a great talk. I really loved it. So this presentation, the outline of this presentation is basically, I'm discussing, just for those of you who are not familiar with BASi, I would just like to introduce BASi Research Products and our collaboration with PalmSens. And then I would like to introduce a product which is kind of tailor-made for wearable sensing. And we would also discuss the need of such a product. Of course, we want to know how good the product is in terms of targeted application, and is there something that can be done with a Potentiostat that you can actually wear on your body. So without further delay, let's start with the introduction for BASi. For those of you who are not familiar with this company, this was founded in 1974 by Dr. Pete Kissinger. In electrochemistry, we say if Dr. Alan Bard taught everybody how the theoretical concepts for electrochemistry, it was this particular book, Laboratory Techniques in Electroanalytical Chemistry, Dr. Pete Kissinger, which kind of is a Bible for everyone to know how to actually conduct electrochemistry in an efficient way. So it started from a small garage, and it was the first ever computer controlled potentiostat Galvanostat, which is BASi Epsilon Eclipse. This is the newer version. The BASi Epsilon was the older version. It is still in existence. We still sell a ton of this. We were the first one to also come up with something called polarography for water analysis, where you can quantify trace levels of heavy metals in water or seawater. We are currently one of the largest global providers of electroanalytical solutions, I would say customized solutions as well. And then now in partnership with PalmSens, we are the providers, one of the biggest providers of portable, wearable, compact or lab scale electrochemistry platforms and accessories. So this is him. He still comes to the office. He's still fit, and he's just received something called a Society of Electroanalytical Chemistry (SEAC) Service Award. He, he basically founded SEAC, in my opinion, but now we have named the award after him. So now the award is also called Pete Kissinger Award. If you are at PitCon, or if you ever come at PitCon, do join us. We have this really nice Society of Electroanalytical Chemistry symposium, and BASi also, of course, provides awards. The Dr. Riley Award, we kind of sponsor it, and then we also do a really nice lunch session. So please do join us if you are at PitCon. So these are the segments where BASi kind of tries to provide complete solutions. It may be basic electroanalysis, or it may be pharma and educational research, or corrosion or electrodeposition. Today's topic is biosensors, and preferably wearable biosensors. So without further delay, I would like to introduce our partners, PalmSens. We are the sole distributor of this company, which started its first ever pocket size Potentiostat Galvanostat. They are famous for the smallest possible electrochemical impedance spectroscopy analyzer. People will think, oh, it's just a size of a matchbox. How can it do EIS? Well, it can not only do EIS, but the software can also do fit and simulation, and it's very sophisticated. So it's 20 plus years in the field with global presence in 120 plus countries. The company itself has 200 plus OEM customers where they actually take this in a skeleton and develop their own reader. Founder of Bluetooth and battery powered potentiostats, essentially. And then right now, I would say the largest provider of biosensor accessories, SPs, and other items in the world. So this is the product range. As you can see, something that you can connect to your mobile all the way to, we have multi-channels, we have multi-palm sense. The beauty of these potentiostats is they are very rugged as well. They are Bluetooth powered. They do a ton of stuff in electrochemistry, and for its compact size, they are very, very famous in terms of their compactness and the power that comes out of it. Say, for example, our Nexus, which is the white colored one, this right here, this is actually having a capacity to apply and measure 1 amp current, and on the lower side it can go all the way till low picoamps, and it can measure it with very high femtoamp resolution. So of course it can do 1 megahertz EIS and much more. So this is the topic. I will not deviate from the topic. We are discussing wearable sensing today. So let's first understand the applications of PalmSens, how actually the wearable sensing kind of came as one of the goals of PalmSens as a company. So PalmSens was always, since last 20 years, we have published a lot and people have used our potentiostats. It's a very, very famous kind of handheld potentiostat, PalmSens 4, which is very famous for variety of applications, going from biotoxin analysis to gas sensing to organochip development. I really like to show this slide because we have Dr. Jessica here. So yes, PalmSens was taken in space, and because of its rugged nature, it successfully was taken. It's one of the only potentiostat that actually was taken in space, and yes, people did space exploration on PalmSens potentiostat. But now we are ready with something called OEM options, where we are providing ready-to-go solutions some of these examples are Lactosense, QSM Diagnostics. All of this, they've started developing their own readers using our potentiostats. So as far as Sensit Wearable goes, the first thing which comes to anybody's mind is why, wearable sensing. It is there out there in the world, but I think I really like this particular review, which kind of explains the next generation wearable sensing technologies. Where are they, and how are people understanding wearable sensing more in terms of chemical based analysis or epidermal skin analysis? So then comes the question that, okay, you can do wearable sensing, but how to develop wearable sensors? Is there a potentiostat manufacturer small enough who can conduct localized tests on the skin, right? Can it be used on any kind of homemade sensors, or is it limited to just sensors that the manufacturer provides, right? Can it do EIS? Because you just saw a presentation on cortisol and how important EIS is for analysis of sweat, because first primary target is sweat analysis. How about skin patches? Can we customize the skin patches according to the curvatures and the shape? And last but not the least, is it cost effective? Is it $1 million, or is it, a portable potentiostat? Can a early stage startup researcher do work on it? So we always had Sensit Smart, which was a portable, I would say, handheld potentiostat of a size of a matchbox, but it's actually a bi-potentiostat that can do EIS all the way till 100 or 200 kilohertz. It has many other techniques, and you can actually do 3 electrode system with a SPE connector. It was always there for next generation analysis. So this is just one of the papers I've selected where few of our customers started doing sweat analysis with this. So this is a nice paper where this portable potentiostat was used for uric acid and tyrosine detection in sweat. And they use laser-induced graphene porous electrodes scribed on a flexible polyamide sheet. So what am I saying? They not only did uric acid and tyrosine, they successfully did pH detection of the sweat without any other analytes. So the concept works, and the idea was, can we have this particular potentiostat made in a more sophisticated way that can be stable on the screen, and it can be hooked up on a screen patch. So another example is this one, where this particular group in Texas, they have done application on inflammatory biomarkers in sweat. So again, a very, very nice paper. Again, the use of polyamide sheet, and then the microfluidic channel for doing this particular analysis. It's really a good paper. The slides will obviously be given to you, and you can obviously have a look at this as well. So the ideas were always there that, okay, we want to do something in terms of sweat analysis, and that led us to invent the wearable bipotentiostat with EIS. So essentially, the overall mission was to accelerate the development of the biosensor to measure up to 2 different working analytes, because it's always important, protein or any kind of interactions, has to be a wireless and autonomous, has to be battery powered. So these are some core requirements, because you want to have a wireless Bluetooth connectivity, you want to be autonomous, you want to have it battery powered, so the battery lasts long, so you need to have a good battery inside it. And then a very good software like PS Trace, which can do EIS, which can do fit and simulation, which can do chronoamp, chrono CV, square wave, all the good old biosensing techniques, right? Most importantly, it needs to come with a development kit. Like, I'll show you what I mean by development kit, where you can actually take it rather than on the skin. You can also do batch analysis if you have some sweat samples. So this is what a Sensit wearable looks like when you take it, and it comes on a mounting bracket. It comes fully equipped in a development kit. It comes in with a patch, or say a bracelet, kind of, where you can actually wear it, and then you can also use it independently on a bracket if you want to do just a drop test of the sweat on your sensor. So we try to provide everything possible in terms of this is the exploded view. It is capable of doing EIS up to 200 kilohertz. It's a bipotentiostat, and then it comes with a potential range of minus 1.7 to 2 volts. Not to mention the current range. It has a very good low current range, 100 nanoamps. PalmSens is very, very famous for it. So yes, it is really, really fully loaded, in my opinion, for wearable sensing. So a development kit consists of everything. So all of this which I have shown you, it is actually included in the development kit, including a Velcro strap with a mounting bracket and a universal SPE connector as well. So we are not hiding anything. We are not charging you extra for anything. All of this is all inclusive. And guess what? Everything is inclusive at a price range. We usually don't provide price range in webinars, but I can openly say this is really, really cost effective. This is under 2000 US dollars. Okay. So in US market at least. So for me, yes, it's a fantastic product, and I would say comes with all the electroanalytical techniques that are required in biosensing. I would say even more. Differential pulse is one, square wave, but more importantly, look at the EIS. You can also do potential scan EIS, and on galvanostatic side, you can also do open circuit potential if required. Yeah, it has a really good software which we do not charge, and it comes, all the future upgrades are also not charged to the customer in terms of cost efficiency. One of the questions in our previous webinars were, are custom wearable patches possible? And yes, we have partnered with companies like ScreenTech, Loma, there's InnovoSense, where we do have options for our customers if they want customized wearable patches. You just have to talk to us and you have to just ask if there is a customized wearable patch possible or not. And that is it for the wearable sensing part. Now, I think we are ready to take your questions. I think we do have enough time to go back to Q&A, and then we can go from there.
Yes, thank you so much, Ritesh. That was great. So we have several questions that have came in. We'll start with this one's a multi-part. This one's for you, Dr. Koehne. And the question is why not using ready-to-use multi-walled carbon nanotubes that are already functionalized with the carboxylic acid groups that are already available on the market in either powder or printed ink?
Yeah, we actually started there. And I wasn't maybe very upfront with our starting material, actually, even before we oxidized it, was with a pre-functionalized COOH functionalized carbon nanotube dry powder. But what we found was that we couldn't suspend it very easily as it came to us from the manufacturer. So we further oxidized it. But yeah, absolutely, depending on the product, and if you were able to find one that was already good to go and suspendable in water, by all means use that. We kind of started in on our own ink manufacturing because we also we're surveying at the same time commercial markets and trying to find stuff that was carbon nanotube products that were easy to use. There's been a lot of development in that space since then. And so it, probably moving forward, we would rely more on commercial products than doing our own in-house development. But in the early days, that's kind of where we were at. What we found and what was working best for us was if we, further oxidized a pre-functionalized product and then suspended that.
Thank you. And can you talk a little about the ink concentration for the results that you shared for the cortisol detection and how you coupled antibody to the sensor for the binding?
Yeah. So the concentration, if we're going to have a Q&A that goes public later, maybe I can get you a better number because, offhand, I think that a lot of our starting processes when we start oxidizing is a milligram per milliliter comes to mind, but I might be off. So, stay tuned and I'll try to get you a better number of what we work with on that. It's likely that I'm not correct and have to talk to the scientists in my lab. Then in terms of the functionalization that we do, it's a very traditional coupling chemistry with EDC and sulfonyl NHS, used all the time in coupling of primary amines to carboxylic acids, and used a lot in this type of carbon chemistry that we've worked with it for quite a while. So it's, yeah, EDC and sulfonyl NHS coupling chemistry.
Thank you. And yes, if there's additional information, we will make that available. We'll make the recording as well as a detailed Q&A available after the presentation to everyone who registered and anyone who might be interested. So next question, have you developed a method to reduce biofouling from the large molecules in sweat? And is there a washing step involved to detach non-specific absorption?
Yeah, that's a really big issue with all biosensor development, and nothing that I addressed here. And so I'm going to talk kind of more vaguely about that space in general. There are chemistries that one can employ on the surface using like PEG terminated short chains or polyethylene glycol, in general. A lot of our sensors will also use the BSA blocking agent. The sensor that I showed you, the data from didn't have any blocking agents or any non-fouling agents to the data set that I showed you, but it's something that we do commonly and are looking at in this space. It doesn't seem that we get as much fouling in this kind of application space as some of the others, but that's I don't know. I wouldn't. Maybe that's just an observation that I've made. I might revise that statement later as I look into it further. But yeah, we will commonly employ different kind of biofouling agents onto our electrode surface. For exactly that purpose. The device AstroSense that's moving forward does have a biofouling agent. It's what is it exactly on that one? It it is a monolayer of well, actually I might get that wrong, so maybe I'll just keep it as, we do employ, and generally speaking it's like a PEG kind of terminal unit of some sort on a surface.
Thank you. And then how are your sensors overcoming the interfering compounds? And what other electrochemical sensors or target analytes are immediately required in the space station?
Okay, good questions. I mean, all have been good questions. So we do interference studies quite commonly. And while I didn't show anything with this cortisol in particular, things we've worked a lot on chemicals like dopamine with uric acid interference, and being able to differentiate those two signals from, say, serotonin. And we've published quite a few papers on that. Some materials seem to be better at differentiating those signals than others, and I've written a paper, at least one paper on carbon nanotubes in particular about that we were getting kind of more distinct peaks of some of these redox species and able to see them distinctly from one another. I'm also aware of groups that are using some machine learning algorithms, trying to differentiate signals that can overlap. And so that's kind of, broadly speaking there. In terms of well, it's not really about non-specific absorption necessarily. Maybe I'll just leave it at that for now. What was the second part of the question?
The other electrochemical sensors that are required in the space station.
Oh, yeah. Okay. Yeah, there's a variety. So we work very closely with our Human Research Program, which is the program that oversees the astronaut health and well-being. And they have actually road mapped out, different technology needs that they have, things that they, well, sometimes it's scientifically things that they need to understand, and sometimes it's mitigation strategies, it's sensing strategies, it's all kinds of different things like that. So we work very closely with them to understand what are those ailments that are of most interest to them. And we target all of our technologies towards what their needs are. And so one of the slides I showed kind of had a variety of biomarkers that were of interest. Cardiac health is of interest. We have a project going on right now for a troponin eye sensor concept that we're demonstrating for them. The stress biomarkers are of interest. They are interested in sleep patterns and circadian rhythm in that space as well. Muscle atrophy is of interest, and so there are different markers. And what I do when I get into this space with NASA is I go to the Human Research Program's roadmap, and I look at what are their concerns and what are their needs, and they have risks, and then they have things that have mitigation strategies, and they have things that do not have mitigation strategies, and I target those. And so it's a good resource to go through if any of you are interested in proposing technologies to NASA.
And another quick one, what is the LOQ of uric acid?
This would be for Ritesh, because I saw your uric acid slide.
You're muted, Ritesh, if you're speaking.
The I would say that is something I need to check back and come back to you. That is not the paper I published. I'm still letting very honestly, that is a paper that one of the customers using our Potentiostat has published. So we would certainly like to show that paper, and I would like to share that paper completely with everybody here so that they can have the detailed look at that. But at this moment, I cannot say the exact number of what is the LOQ of that.
So we'll get back. We'll include that in our full version of the Q&A. So here's another one. I'm currently working on bisphenol A detection in aqueous solution. My team has achieved good results so far. Now we are targeting detection in human blood, and I'm looking for information, wearable sensors perhaps, which could help me. Any thoughts, or is this one we could?
I was thinking this was a Ritesh question, but maybe not. Maybe state the question again.
So they're working on bisphenol A detection in aqueous solution and looking at targeting in human blood for the next round.
And so looking for wearable technologies to help them with this application. And I guess,
Yeah.
I think, Ritesh, spoke to a lot of what they have, on the market and solutions that they work with customers on. So that's
Yep, of course. Yeah.
Yeah.
The bisphenol A detection, we do have a lot of customers targeting this. Now, if you are doing, it depends. What is the overall goal here? It depends upon what is the detection limit that you want to go at. Yes, we do have customers who are targeting this in human blood plasma. It is not that easy. To be honest, there is interference. You are also looking in terms of wide variety of pre-processing, and you also want to know essentially, are you trying to develop a reader out of it, or are you trying to develop an inline monitoring system out of it? Those two are two completely different concepts. So if you are looking for a reader, and then we suggest a OEM based Potentiostat, and then we suggest something in terms of those lines. But what I can do is, let me share my screen one more time and let me take you to biosensor page. Give me just 1 second. This is the easiest way to search if uh, PalmSens Potentiostats. You come on PalmSens website, and under the support, you just go for scientific publication. So I'm pretty sure I'm actually not here. Can be here. And I'm pretty sure something will come up here in terms of who has done what. So suppose someone like this, where someone has done a functionalize this kind of sensor for environmental hormone, and you can go through this one and definitely you will find something. This is an interesting paper. I have actually read this one. It's a smartphone assistant electrochemical sensor for trace bisphenol A detection. They are actually working, in my opinion, for bisphenol A in blood. This one is also a very good one. So I would say this is the easiest route for you.
Awesome. Thank you for that. So we are at time. However, I know we were discussing beforehand that both Dr. Vyas and Dr. Koehne have a little bit of time to stay on to answer questions. So if you cannot stay on with us, we'll make sure that you get all the information and the answers to the questions that have been asked. And if you do have some time, we can stay and continue the discussion. A little bit longer. So maybe we'll go back to some of the cortisol questions. And what was the matrix you were, in what matrix were you measuring the cortisol?
Yeah. So those measurements are not performed yet on the body for the ones that I showed you, and they're in an artificial sweat that we purchased commercially for that one. We when we're doing our developments, we measure everything from just kind of a standard PBS as we're getting started and kind of optimizing our sensor, to artificial sweat, to eventually moving into real sweat. Also something not shown today just because it's under development, but we do have an active sweat harvesting technology that we're printing and demonstrating with our wearable AstraSense sensor. So that's just another part of the puzzle here, but it's just not published yet, so I didn't show anything from it.
Do microgravity or radiation also affect things like cortisol sensor readings, especially if you're using impedance-based methods?
Yeah, well, we've been most concerned, of course, with the manufacturing, and especially microgravity, as it affects the manufacturing of the sensors. And so that's been a key thing that we're looking at with all of our printers that we've been developing with outside small companies and academic partners. We as well as the sensor operation, fluidic delivery systems and what have you are something that's always on our mind, and something that we're minding when we move from a ground-based system to a microgravity test. So those are the things that are most on our mind. In terms of the cortisol itself and influences because of microgravity, I'm not sure that we would expect to see anything there other than the stresses of a space flight mission in general, and what the tasks are for that crew member. And that is part of the reason for the development of the sensor to use during flight.
Thank you. And can you talk a little about the stability of the sensors? One-time use, or can it be used multiple times?
Yeah, what I showed you, the data for today, I would be comfortable with one-time use. So it's not real conducive to a long wearable, kind of application. And what is under development is a sensor that can bind and unbind cortisol over time. And we are looking at long duration use of that particular style sensor. And so our goal is to have a sensor that can be wearable throughout the day. So say an 8-hour time period that we can ping at multiple time points during that day to understand what the cortisol levels, how they're changing for that specific individual. But what I showed you today would not be that. I would more comfortably say a one-time use sensor.
So, how would you address the issue of reproducibility with the printed electrodes?
That's a good one. Um, It is a challenge. And, my lab was really predominantly, focused on very precise lithographically defined structures in the past, and precise control of where our materials were placed and grown on substrates. So that's been a big change, from having that kind of control to, a printed format. All of our sensors, and so actually it is a big part of what I did not show, but is a lot of our characterization is getting sensor to sensor reproducibility, and having ways that we can offset for any slight variability in our measurements, so that we can make reliable measurements per every sensor that we have. But it's a challenge when you go from say photolithography to inkjet printing. It is less controllable.
Could you share your thoughts on using aptamers as receptors in terms of its longevity or reliability for wearable application? And have you found in other types of receptors to be effective for on-demand sensor fabrication and space missions?
Yeah. So our current development is with aptamers, and so I've done some aptamer based biosensors in the past. I'll say a couple of things about aptamer based electrochemical sensors, and I've used them for kind of a variety of different sensing schemes, shall we say. So I've used them very much in the same way that I'll use an antibody. So like the data that I showed you today, and we've been able to electrically address them to kind of unravel, if you will, so that we can unbind whatever it was that we were detecting and get it to rebind. And so we published a paper quite a few years ago that demonstrated that. We're also interested in these electrochemical aptamer biosensors that have redox tags to them. These are sensors widely in the literature, especially the Plaxco group, where they're kind of moving as they bind, and a redox probe's proximity to the electrode's surface changes. This is something that we are looking at right now. So I love working with those types of probe molecules. They're very, very stable. You can reuse them over time. And so we love working with aptamers when we can find a good aptamer for our application.
All right. So you were mentioning about energy harvesting and storage aspects in your research. How important is the need for self-powered electrochemical wearable sensors in space missions in general?
Yeah, it's development that's going on concurrently. What I will say is that for our first proof of concept prototype, we're still relying on commercial batteries, and there's some commercial printed batteries even that are coming out on the market that we've started screening. And so that's probably what we'll do first. But we are looking at manufacturing our own structures, batteries, supercapacitors, different types of harvesters for those applications in the future. But it's much more still on the research side of things, and we have solutions commercial around that right now. So that's kind of what we're relying on for our initial demonstrations with the sensor.
And how does the conductivity of the electrodes change over different layers? Also, the conductivity gets affected by switching from paper to Kapton.
Yeah, well, it's basically, the less material you have, especially if you think of carbon nanotubes, this network of these, tube structures, you'll have, less kind of discrete overlap with them, as you have a thinner film, you'll have more breaks in that film, shall we say. And so it's important to have enough layers that you've got good connections between, all of the nanotubes and your sensor film. When you move to paper, paper is porous, and so that material will just kind of sink into the paper and coat the paper fibers themselves. So it changes the performance quite dramatically, actually. And you very, very quickly get to this kind of three-dimensional electrode surface when you move to paper, which can be, good and bad depending on kind of how you're planning on using it, but it changes because paper is porous and three-dimensional.
Awesome. And we might have already talked a little bit about this, but for cortisol sensing, how do you make sure the antibodies remain in structure for prolonged monitoring in the space station?
Yeah, well, I'll kind of say that we don't at the moment because that was a proof of concept for that particular application, but we've moved to actually what we talked about before, an aptamer-based approach going forward. So we just haven't really evaluated the antibody-based systems very in depth for space applications.
Have you tried 3D printing for developing any of these sensors?
Yeah, there's, because we were talking about the wearables, I didn't talk about any of this, but we also use 3D printing, SLA printing, as well as FDM style printing to manufacture a lot of fluidics to couple with electrochemical sensing. I have quite a few 3D printers that are utilized for all kinds of different applications. We have, Cricut tools for cutting, and we make gaskets to seal things. So we tried to get as many of these kind of additive manufacturing tools that we use to prototype different devices, different instruments as we move along.
Awesome. So someone was very taken by this. The question is there any opportunities for internships or other ways to participate in the NASA project? And if so, how could people get information about that?
Yeah, I'm kicking myself right now because I usually put it on my last slide, but intern.nasa.gov is the website. Intern.nasa.gov. No and anything else. And that is our, they call it our one-stop shop for all internships. And this is across the agency. It's not just NASA Ames. And so that's where you go to find out what opportunities there are. We offer internships in the fall, in the spring, and in the summer. And we have a very vibrant internship program. So I encourage any of our young people, trainees, please look into our internships. We have internships for undergraduates as well as graduate students. There are fellowship opportunities, and you can find all the information on that one particular website. So please check it out. I work with a lot of interns, so would love to see some applications come out from this talk.
Great. Awesome. Well, thank you so much, Dr. Koehne and Dr. Vyas. This was a great discussion, great presentation, very interesting, very exciting.
Um, Nicole, just I wanted to not end this one without answering that LOQ question. So can I just
Oh,
share the screen? I actually found that answer
excellent.
as well. So guys, this is the paper. It's online and it's open access. It kind of very nicely discuss how they've done uric acid and tyrosine, and they have managed the detection limit, the sensitivity, all the way, I would say, up till 0.071 micromolar for uric acid. And then for tyrosine, it is 0.026 micromolar. It's pretty good. I think the Potentiostat is capable of doing all that is required for low scale detection. It comes with a nanoamp range. So it's dedicated for that kind of, because we give a 1 picoamp or say that 10 nanoamp kicker when people measure, when our customers measure low currents. So it's actually a good question where, you know, someone on wearable sensing on those kind of detection, they can still manage this kind of detection limit. So that's the answer. Yeah.
Fabulous. Thank you. Well, and thank you to everyone who stayed on, spent an extra 15 minutes. This was awesome. And again, we will make sure that everybody gets copies of these materials. And we look forward to seeing you at our next webinar.
Thank you, Nicole, for moderating.
Yeah, thank you for the invitation.
Hey, thank you. Thank you, everyone, for participation.